So very, very good morning. Thank you very much. I used to be a professor, so I need to walk around and talk to people. First of all, I want to thank the program committee of ISPD to allow me to come back to my roots. As was mentioned, I used to work on EDA when I was a professor at the University of Illinois. I started working on parallel algorithms for EDA. All those 350 papers that you talk about, those were my PhD students. I had one student working on parallel placement, parallel routing, parallel synthesis, parallel test, parallel, etc. Unfortunately, when I worked on those problems, nobody cared about parallel. People, the synopsis and cadence say, hey, this is not relevant to us. As it turns out, I used to be CTO at ANSYS, and I will share, ANSYS revenue was about $3 billion. And about $500 million of that revenue came from the HPC licenses. So making the ANSYS algorithms run on high-performance computing, I will not talk about HPC, but our Fluent code runs on 200,000 cores in a scalable manner, right? That is, and people do pay for it, right? Because they see the value. So my message to all the people in academia is, it might look like your things are not relevant. Just wait 20 years and it will become relevant. So today I'm going to talk about AI/ML. And I know this is a ISPD thing, so I should only speak about physical design. But I want to give you a bigger picture of what is happening in the world of intelligent systems. And so my talk will have three parts. I'll just do a quick overview of intelligent systems because I really want you all in academia to understand what is going on in the world of intelligent products. And why did Synopsys pay $35 billion on acquiring ANSYS? And it's a super, super exciting field. And again, physical design is only a small part of it, but it actually has an implication on the larger system. So, and then I will talk about AI/ML applied to simulation and AI/ML applied to EDA. And there's sort of two broad things that I will talk about. One is to make the simulation go much faster. In the world of simulation, we do what is called for partial differential equations, PDE solvers. These solvers take like ridiculous amounts of time, like 10,000 hours to run, right? So using AI, can I speed up simulation? There's a big emphasis, and I will talk about what is used there. And the other thing is using AI to improve the workflow, make our tools easier to use, which is sort of tied to all the work on agentic AI that we heard yesterday, right? And then I'll talk about AI applied to EDA. And actually, I don't even have to give my presentation because there was such a fantastic panel organized by Andrew yesterday with Chuck and Ankur and everybody. So it will be a repeat of what you have seen, but I'll just talk about the Synopsys perspective. And Igor did a fantastic job representing the Synopsys part. So the second part of my presentation will be sort of a repeat of the great panel discussion we had yesterday. So my apologies. So let me talk about the opportunity about intelligent product or intelligent system design, right? I mean, you all hopefully drove a car to Bonn, or you took an airplane or a train, right? These products are no longer mechanical products. They are software-defined products. Means the Tesla car has 100 million lines of code which runs the controls algorithm to make it do autonomous driving or self-parking or whatever, right? There's a software that is running on it. And that software is controlling the hardware. So it's a hardware-software interaction that is inside the software-defined vehicle, the software-defined data center, the software-defined drone, the software-defined airplane, and so on. And I want you to understand that this complicated system is now being designed by the EDA tools from the Siemens, Cadence, Synopsys, etc. So this is the world that we live in. So let me just deep dive on one of those products, a drone, right? I'm sure you guys have seen drones, you have flown drones and so on. But just let me share with you what is involved with the design of a software-defined drone. The drone, as you know, has sort of blades that will fly, right? And those things fly, and because of it, it generates the lift that lifts the drone. So the mechanics, the fluid dynamics of, you have a rotor on the blade, and because of that whizzing at 200 whatever revolutions per minute, right, that thing lifts. And so you have a certain weight and it lifts. That needs to be modeled by, in our case, a tool called Fluent that does the fluid dynamics. But then as the rotors are going around, right, it's creating friction, the blades are bending and so on. So that mechanical thing needs to be modeled with a tool we have called ANSYS Mechanical. Then because of it, you are generating heat. There is thermals, and that thermal needs to be cooled, right? You have air cooling, liquid cooling, or whatever, not in the drone, right? In general, right? So that needs to be modeled with the thermals. And then you have electromagnetics interactions that are happening, right? So that the EMI, EMC that is going on in the drone, right? As you're sending signals to control it, that needs to be modeled with the EMI, the electromagnetics. Then this drone, right? All these drones that are being used in the war, right? They are autonomous drones. There's a piece of software that is written there, right? That software may be 100 million, right? Not 100 million, so 10 million lines of code. Now, you are writing the software on a ECU. There's a chip from an ARM-based CPU that is still not yet being designed. It will be designed with the Synopsys, Cadence, Siemens tools, right? So there's a chip has not yet been built. But the software that you're writing, you would like to emulate that software on that Zebu platform that Helena talked about yesterday, right? So we are writing this thing, so you want to emulate that software. And that software that you're writing, right, you are trying to do a drone that will fly. I'm giving a bad example, right, from, say, Ukraine to Russia and back. And that thing is a mission engineering, digital mission engineering, right? And then the chip that you do has to do a EDA too. So the entire thing should be done on the computer digitally before you fabricate anything. This is the incredible opportunity. And to do it, it requires multi-physics simulation, right? Simulating the fluids, the mechanics, the thermal, the electromagnetics, right? And the software control and the software emulation. This is the incredible opportunity, and I want you to be all excited about what we are talking about, right? And this is precisely the reason why Synopsys invested $35 billion on ANSYS, right? Synopsys was a leader in the EDA world, in the world of electronic design automation and IP, like Cadence, right? But by combining it with the ANSYS, which was a leader in system-level simulation, right, with all the mechanical and fluids and electromagnetics, right, the combination of those allows you to now build digital twins purely on the computer, right, powered by emulation, etc. Right? This is that intelligent product design that I'm talking about. So where we have landed with this is this incredible list of Synopsys tools, which is the EDA tools, the tools that many of my Synopsys colleagues here are working on, right? From sort of the placement and routing tools to from physical design, right? Inside the RTL synthesis with Fusion compiler, and then once you do the implementation, you essentially do the sign-off to prime time and the timing sign-offs and the power sign-offs and all those kind of, those are the EDA tools. And then on the right-hand side, you have all the ANSYS tools, which is all the world. As CTO at ANSYS, I was driving, right, around the physics, the structural simulation, ANSYS Mechanical or LS-DYNA, the fluid simulation, Fluent, the electromagnetic simulation, HFSS and Maxwell. And it's this incredible combination of these two things which will allow us to build intelligent systems. So, in my role as sort of CTO of the combined company, right, which is trying to look at this opportunity, the purple shows the sort of Synopsys tools. Again, the Fusion compiler, prime time, there's the testing, etc. tools, and the orange tools are the tools from ANSYS, right? Those are the products. But what is the technology that's driving these products? So there's sort of 4 layers of technology that I am trying to drive, right? And the The bottom layer is the computing layer, right? Again, I don't know if you guys heard Jensen's keynote yesterday, right? Where he talked about the $1 trillion opportunity, right? He basically said it's accelerated computing. I mean, this is essentially what I was trying to do 20 years ago, parallel algorithms for EDA, right? Taking the different software and making it run on the CPU. So it originally ran on a CPU, an x86 CPU, right? Or one of the Solaris CPU, whatever, right? On a Sun or whatever workstation. And then when the clock frequency, when Moore's law would take care of the frequency and the transistors and so on, right? You don't have to do anything. Just wait 2 years, it'll be a faster processor, right? And a faster thing will run synopsis and cadence and so much faster. But there was a time when the clock speed flattened at 2 gigahertz and you couldn't get any more juice out of it. You were forced to do parallel processing, right? And so the early work on parallel processing was you took 1 core, did 2 cores, 3 cores, 4 cores, multi-threading, right? Which essentially took the same code that you write with our synopsis tools, our cadence tools, and so on, and it automatically, dynamically finds out where the parallelism is, right? And you can get up to maybe 4-way, 8-way parallelism with no work required from the applications. But then what we found was, well, that was limited, and so we started working on shared memory parallel programming. We took a code written in C or Fortran or whatever, and you said, I'm going to now spawn different threads, run them in parallel, right, with locks, unlocks, and so on, use programming directives like OpenMP and so on, and that could scale up to maybe 64 processors. But that, it was limited. And then you said, well, now I want to scale even more, and so then you have to do message passing, distributed memory, sending messages to each other, right? And that allowed Fluent, for example, to scale up to 200,000 cores, right? And that was a big deal. But then came GPUs from NVIDIA, right? And you say, okay, let's do fine-grained parallelism where there's like 16,000 cores on a CPU itself, except that these cores all go in a data parallel way. You have to all go left, all go right, like SIMD parallelism. That required you to completely rewrite that code. And as Chuck was saying yesterday, right, you have, I mean, this kind of GPU parallelism is something that we have to really rethink. And I was happy to see yesterday one of the ISPD talks was about GPU parallelism, right, of this placement routing. So this is incredibly exciting. But then what's beyond this quantum, right? And my friend Igor talked about quantum. With quantum computers, you can actually go with qubits, right? With 10 qubits, you can go to the power 10, 1,000 times speed up. With 20 qubits, you can do 1,000,000. With 30 qubits, you can be 1,000,000,000. With 40 qubits, you can be 1,000,000,000,000. You get 1,000,000,000,000 times faster, right? So just imagine placement algorithms, right? All of these are NP-hard problems. I just want you to imagine what is the potential of quantum computing if it can solve these kind of problems. So that is at the core computing layer. And I'm not supposed to talk about it, but this is like, I dream of parallel computing all the time, right? And then it's the next layer is the engines layer, right? Which is what this whole conference is about, right? Doing the placement algorithm, all the conjugate gradient placements, and the bond route that you heard, and the prime time and fusion compare and so on. Then the next layer is platforms, and it's an incredible opportunity where you can build sort of tools and multi-physics workflow using PyAnsys or Fusion and so on. And then on top of it is the workflow. That is the agentic workflow that everybody is excited about. So this is what I'm going to talk about. I'm going to talk about the AI part today, right? And AI to accelerate simulation and EDA, right? To speed things up, and AI to make it easier to use so that it can build better chips. So with that, let me first talk about AI applied to simulation. Again, I know that this community does not every day think about simulation, but it is an incredibly exciting area, right? So the world of simulation that we deal with, in the circuits area, you all know about circuit simulation, right? Which is sort of first order. You do C, dVdt, L, Li, didt, and sort of single derivatives. In the world of physics, these are second-order partial differential equations. So you have x, y, z, 3 dimensions, and now you're trying to solve Navier-Stokes equations for fluids, or structural problems, Euler equations, or electromagnetics Maxwell's equations. These are DVD2, all the kind of stuff, right? These are analytical, you cannot solve them. So you solve them numerically. So what you do is you take a structure and break it into, say, 4 quadrants, 4 finite elements, and try to solve those 4 finite elements, that equation, numerically. If the results are not good enough, accurate enough, then each of those rectangles, you break it up into even more rectangles. Do you like it? You don't? Okay, let's do 16 by 16, 20, 30 by 30. We keep increasing the number of elements. At some point, the accuracy of the finite element method is good enough. So, okay, this is good. This is what accuracy I want. The trouble is, every time you increase your number of finite elements, essentially it becomes solving like AX equals B. So the number of rows and columns in this matrix just goes through the window, right? So instead of a 1,000 by 1,000 matrix, a million by million matrix to a 10 billion by 10 billion matrix, and imagine inverting that matrix. It will take you 10,000 hours to run. So in that world, that is when I joined ANSYS, right? And everybody was working on numerical methods. And I say, hey, this AI thing is pretty cool. Can we use AI to solve this problem? And that's sort of the first thing that I worked on when I joined ANSYS as CTO. So here is a problem. You have a solver. It's a fluid solver. And here is a SUV, a truck or whatever, and you're trying to do external fluid flow. This fluid, the air is going around it, and you're trying to come up with a design of that SUV so that it will minimize the drag. That's the problem. And you solve it with Fluent. It turns out that one run of Fluent with the initial condition, give it a CAD, one run would take you maybe 1,000 hours or 10,000 hours. It just takes forever. So now this problem with AI, the way it was solved is, well, take an initial condition, boundary condition, a design, and you assume that you have a neural network, right? A 3-stage neural network. You start with absolute random weights. You don't know any of the weights, and you guess them, and then you predict the output. Obviously, the output will be garbage, right? You have a garbage in, garbage out for the first result. But then you actually run Fluent on it. So you take that run of Fluent, that garbage result from the neural network, there's an error. You try to fix that error, do back propagation to set the weights of the neurons so that it is 0. That's your first step. The next step, you give it another initial condition, another boundary condition with the previous weights of the neural network, right? And now again it's an error. You try to fix it again. Essentially, you're doing stochastic gradient descent, right? In the optimization, you have some point and you're trying to bring it down to 0. And once you bring it down to 0, you have converged, and that's your result. So this is basically what we are doing, right? But again, there's a lot of things I'm just going over, right? But this is at the core of using AI to learn the physics. You don't have to do any numerical methods. It is just run any solver, run Fluent, run mechanical, HFSS, whatever, or the multiphysics, and it will just give it the result, right? And that is the SimAI platform that we have. Now, is it accurate? Sort of. It's not really accurate, but it's pretty accurate. So where does it get used? It gets used in the format that remember that SUV problem I was talking about, right? That SUV, a designer at Mercedes or BMW is doing all kinds of different slight tweaks to that CAD so that it minimizes the drag. You have to do tens of thousands of designs, right, CAD designs, and run Fluent on every one of them. Of the 10,000 different designs, each one taking 1,000 hours, it's like 10,000 hours, right, 10 million hours. It's a lot of compute. So if you can take those 10,000 runs, and each of the runs, you do it in a matter of minutes. So most of those evaluations you do very quickly, and then you come up with 3 designs. It is this SUV with this thing and so on. Those 3 designs you have to do with full validation. So the workflow is use AI to learn the physics, use that AI to do design space exploration quickly, very quickly, lots and lots of designs, and then last 3 or 4 or 10 designs, do full validation. That is the workflow that we recommend to our customers. So this is all about speeding up the simulation. But here, there is a designer at Mercedes or Volkswagen, in response to this thing, say, hey, there's too much drag. I need to change the mirror with a slightly different CAD to change it. Turns out, AI can do that job. And there's a thing called GeoMAI, which says, yeah, I look at a geometry of a CAD of that mirror, or that impeller, or this thing, or this e-motor, and through AI, Gen AI, I will suggest the different CADs. Here is a CAD of a car, right? And it will suggest different CADs, right? So all kinds of different things. And each CAD I suggest, I will simulate to SimAI. So it's like, now people are talking about agentic AI, right? So essentially, there was a human doing the CAD, there was a human doing the simulation. Both are now being done by the AI, accelerated, right? And now you have this accelerated loop. So that's GeoMAI. So now it turns out that these things require the customer, you have to have, like for SimAI, you have to run the simulations and train the AI models. The future direction, this is something that is now being cooked in my CTO office, is to say, can we do foundational models? Everybody talks about foundational models for say, words as tokens, right? What is ChatGPT? It's foundational. It looks at all the words in English language, all the prose, all the poetry, etc. And based on looking at this, says, when you have a sentence like Mary has a little, and it will prompt it, say, lamb, right? Or I wish you a merry, and it'll say Christmas. That's foundational models, right? It is trained on all possible geometry, poetry, all possible English, every magazine article, every paper in ISPD, etc., right? And that's what DALL-E has done with images, right? So he has looked at all the images on the internet, right? And he has grabbed it, and now with Gen AI, so you could ask, you can search on Google to say, is there a picture of a plane crash into Golden Gate Bridge? Now, if, God forbid, there was a plane crash, there would be an image of that plane crash. But with Gen AI, you could create an image of a Boeing airplane crashing into Golden Gate Bridge. Right? That's the text, and will generate that thing. That's what DALL-E does. With Sora, you could actually generate a video of 100 monkeys dancing with 15 elephants in Serengeti Park, right? That is Gen AI for videos as tokens. So in our world of physics-based simulation, there's XYZ, 3 dimensions, and that vector is a pressure vector, or a strain vector, or a stress vector. So imagine if you could actually go and measure all these things in the world, right? If somebody could actually take an oscilloscope or whatever and measure the pressure, temperature, whatever around the world, that would be the equivalent of foundational models for physics, which is impossible. You just cannot do that. But you could do it with a physics-based simulation, with tools such as ANSYS, or Siemens, or Dassault, or Cadence, right, Beta CE. You could actually recreate that data, and by recreating the data for all possible CADs, right, you are essentially doing a pre-trained model. That's the foundational model. Now, this is like if foundational models for text takes 1.9 trillion parameters in ChatGPT version 5, this is like 100 million parameters, right? That's the complexity. But if you can do it, then you don't have to do this SimAI anymore. You upload a CAD, boom, it will give you the result. So does it work, right? Again, this is not a product. This is just, I'm showing some results in a lab. It turns out by looking at synthetic data, you could actually program the large physics foundational models for fluids, right? And you give it a plane with 2 engines, it gives you the result, right? With Fluent, it is giving the ground truth, and with large physics models, it's giving a prediction. Now you give it a car, you give it an SUV, you give it a truck, right? So you're not doing SimAI, you are not training it with car models. You have done a physics model, large physics model of fluids, and you give it a CAD outcomes, right? So this is like super duper good, right? Just imagine, and this is now running at an incredible amount of speed. So I just want to give you an example of what is going on. Now, it turns out the next thing that you can do is you can build digital twins, that intelligent product that I talked about, software-defined, that vehicle, drone or whatever, right? All those products, you could actually build a digital twin of that product. Now, when I was CTO at ABB or Schneider Electric, I used to be responsible for building digital twins of their products, of the ABB robots, or the Schneider's EPC systems and so on, right? Those the APC systems for data centers, right? So it turns out the way we build those digital twins were based on, you put sensors on the assets, and you pull data from those assets, and those time series data is what you are pulling in, and based on it, you are trying to build a digital twin, means you're trying to predict what is going on. That is accurate to about, say, 80%. And we found that it flattened at about, it's very good, that digital twin model based on pure data, right, that you're measuring from sensors, but it flattened at about 70 to 80%. And that was when I moved to ANSYS saying, you know what, you could actually simulate the physics of that robot or that whatever, right? And if you do physics-based digital twin, then the accuracy becomes 90%. If you now combine a combination of data and this thing is called hybrid digital twin, or what we call twin AI, you get like 98 to 99% accuracy. That's what we have today with our hybrid digital twins. And so the workflow of hybrid digital twins is shown here. Again, these are details, but they, again, combining AI with all the stuff that I talked about with sim AI and surrogate models and so on, combining it with data analytics is what we are now using to build digital twins of every one of those products that I showed you in my first slide, right? So then we said, no, we are still not acquired by Synopsys, right? So we are working on, okay, so what else could we do? Well, it turns out that with AI, you can make workflows easier to use. So we have a lot of tools. We have tools like SCADE, which can do embedded software generation, or Fluent, which can do fluids simulation, or mechanical that can do structural simulation. So those are products. It turns out that when you're running Fluent, right, they have to use mosaic meshing or pi meshing and this meshing. You have to have a PhD from MIT to know which settings to use in our Fluent. Once you use those settings, it will give you the best possible result. Except that half the time, the customers didn't know what settings to use. So we have a lot of smart application engineers who actually work with customers and say, hey, I'm struggling, I'm at Cummins, I cannot get this thing. Oh, there's a question, there's an answer. There's a question, there's an answer. We essentially took all those questions and answers and we stuck it into sort of ChatGPT, and we had our version called ANSYS GPT, and now it became the engineering copilot, which is saying it's an interactive tool. You're running a tool and you're struggling and it's giving you guesses like, hey, you should do this, right? So it makes you a lot more productive. That's essentially where all the discussions on agentic AI have gone, right? That's essentially in this area. And then we got acquired by Synopsys. And now we say, wow, this Synopsys thing, they have been doing this amazing thing on agentic AI. So all this stuff is now getting integrated within the Synopsys engine. Which brings me to my next part of my presentation. So I'm perfect. I will be able to cover it. So now let's talk about AI applied to EDA. So in the world of EDA, now, I spent a lot of time in the previous part because I knew this was new material. This is like, you guys sleep, dream about it, right? So you know the stuff. In the world of EDA, you start with a specification, you do architecture specification. Hey, I'm doing a GPU with all these number of stuff. I'm doing the Banerjee chip or Blackwell chip or whatever, right? And then once you do that RTL, Verilog, you do a verification using tools like VCS from Synopsys or similar tools from Cadence and Siemens. And then you do the test, right? You generate test vectors can you test it up, right? With tools like TestMax. And then you do the implementation, like the RTL synthesis, fusion compiler, design compiler, placement routing, all the Innoverse and different types of tools, right? So you know these things. So and then you do the manufacturing of that chip. That's the workflow. So in that workflow, can I use AI to, as Andrew said yesterday, right, in that panel, now I'm essentially going to borrow stuff from that panel discussion. It was amazing what we heard yesterday, right? I have no new content to talk about because essentially the three major companies, like Synopsys, Cadence, and Siemens are using similar approaches, right? I mean, you heard from Chuck about the workflow used at Cadence. You heard from Ankur. Ankur was my colleague at ANSYS. So I mean, essentially, this is commercially what is going on, right? So in this world where Synopsys started was, let's say, suppose you're running Primetime or Fusion Compiler, or you're running this. There are a whole bunch of settings you have to use to make it give a better, right? And people, yesterday it was, oh, I write an RTL, and two different people write two different RTLs, right? And you're doing all these different tweaks, and based on it, you get a different result, right? So in the world of AI, right, you're doing something, in response, either you are improving your PPA or you are making it worse, right? So if you're improving, that's a reward. If you are making it worse, it's a penalty. So you do actions, and in response to that, you have a reward or a penalty. And this is how reinforcement learning works. And I know you guys all know about reinforcement learning. So that's pretty much what was used in our DSO, Design Space Exploration tool, right? Which allowed us to have better PPA, et cetera, right? So the journey was, we started with DSO, and it gave, I mean, I'll have a separate slide on DSO itself, right? The kinds of examples that you had 12% total power reduction, you had less area, improved DRC, et cetera, right? So DSO was successful. That was started in 2017. Well, it works for digital design. Does it work for analog design? Yes, it does. So that was analog space optimization, ASO. Does it work for test? For test max, for testing? Yes, it works for testing. Does it work for verification? VSO. It works for VSO. So it turns out all the flows that I talked about in the previous slide, starting with architecture to verification to testing to manufacturing, the same workflow, reinforcement learning actually works. So let's talk about one particular thing on DSO, which is kind of relevant to this ISPD group, right? So when you are looking at library characterization, right, you have a particular design where you are at the leakage power. You're trying to do this network slack, right? So when you're doing STA, you have to minimize that timing slack, and you have to look at the total slack, and obviously you have to make it as low as possible. So you're trying to get a design with minimum TNS and minimum power. So the original thing was stuck at a particular point, but with DSO, by looking at thousands of different designs, automatically, by changing a parameter of this, etc., it found a solution which is 30% better. That is what Andrew was talking about, right? Using these tools, these AI tools, can I do a better design? Yes, it does a better design based on automation. Second example, I mean, other examples of DSO, right? For different chips, right? There's a chip for an image sensor. Again, you can see the customer is Sony. So you have a 28 nanometer image sensor, and through DSO, it was able to do 12% reduction. You have an automotive chip from 7 nanometer automotive CPU, ECU, 3x productivity. You have a 4 nanometer mobile SoC, a 6 nanometer mobile SoC, across customers from AMD, Intel, MediaTek, Microsoft, et cetera, right? Large designs, small designs, DSO actually has shown improved value. So does it work? Yes, it does work. So an example of taking a large RISC-V core for a data center customer, right? You have a large design, and here is the design, and you're trying to get it to work with maximizing the performance within the power envelope of 30 megawatts, right? So with the default out of the toolbox, right? So basically, if you take a standard reference flow, you would get a design with 1.7 gigahertz. With these DSO kind of tools, right, you get it to 1.9 gigahertz and 27 milliwatts. So essentially, DSO does work for this really high performance data center design. Other design is you have to do this kind of node shrink, right? So you have a product at 6 nanometer, now you do it for 4 nanometer. It's a lot of work, right? Trying to do all these things, right? It's boring, hard engineering. Does it work? Yes, it does work. Again, you run DSO. It took that problem at 2.1 gigahertz, again, using this for 10% reduced area. So that's the power of these AI tools, right? But this is all ML, reinforcement learning. So now the big picture is you have AI applied to the engine itself. You have tools like placement, all the work that you're talking about in ISPD, the placement rules or the routing tools, bond route and so on, right? There's AI that you can use in those tools. And those are AI integrated within the tools. Then there is AI in the workflow, right? As you are trying to design a workflow using Fusion Compiler, whatever, that there is AI in that. Then there is a higher level thing in the actual design of your chips, right? I showed you design of the data center CPU, the RISC-V core or whatever, right? And then the even higher thing, process technology about libraries and captures and so on. So AI is now being used across the entire workflow, and I'm sure there are papers that are happening at this year's ISPD, DAC, ICCAD, and so on. So this is the world of AI. So I wanted to kind of now talk about where things are headed, right? And again, this is the part where all three companies, Siemens and Synopsys, Cadence, Ankur showed a similar slide deck, and Chuck showed the same thing. So there's nothing new here, but the new thing is that industry is now, this is not left to the academic thing. This is actually being used, right? So the journey is, it started with ML inside the tools, right? All the techniques that are being used within the tools, ML enhanced prime time, ML enhanced Fusion Compiler, ML enhanced ICV, our version of Calibre, right? And then using this AI as an optimizer, the DSO, design space optimization, analog space optimization, verifications optimization, test optimization, all of those things, ASA, VS, et cetera, right? And then AI as an assistant. This is where we are today, right? So you heard a lot of discussion yesterday in the panel about this assistant, that assistant, and so on, right? And so there are runtime assistants and there are creative assistants, right? Hey, I want to create a test bench, right? I want to do verification. You spend a lot of time on verification, writing test benches, so those things. The end state is full automation with all the multi-agent workflows. So some examples of assistants that are now in hands of customers, right? As the first one is assistive agents, right? So you have a knowledge assistant, like the example I showed with Skate or Fluent and so on, right? You are running the tool, and based on the interactions, previous interactions, you are saying, hey, I think you should do this, I should do that, right? So that's using the knowledge and helping the customer in the choices. Next is the creative thing. I am writing an RTL, right? So there's things called spec to RTL. I write my specification in English and it will generate the RTL, right? Or I'm generating RTL, what's the test bench, right? To help you in a verification. So creating the RTL, creating the test bench is the assistants that are happening. And the end state is automation, right? And that is where all those things that Chuck talked about and Andrew talked about is in this area with all the multi-agent, et cetera, right? So we had our Synopsys Converge conference last week, and our CEO kind of talked about this journey, right? The level 1 to level 5, borrowing from the autonomous driving area, where level 1 is just assisting the driver, right? Hey, I'm doing cruise control, right? Or I'm doing self-parking, right? To doing all the way to full autonomous driving, the Waymo cars driving around the streets of San Francisco, right? Is that possible? That is the dream, right? We are all working towards that multi-agent workflow. Our term is sort of full autonomy. So we have got some actual agents here, right? Examples of the knowledge assistant, which I showed 2 slides ago, right? You have a tool like Fusion Compiler, and inside the tool, you're asking some questions, and it just gives me a quick answer for prime time, for VCS, for a workflow assistant, right? Generating all the scripts, those tickle scripts that we heard in the panel yesterday, right? And then run assistant, right? Actually helping you run the tool. So this is sort of the journey. So Our CEO last week talked about the era of pervasive intelligence, right? You are looking at AI and software-defined systems and so on. So the world of intelligent system that I showed, right, is going to be software-defined. You'll have 100 million lines of code in your Tesla car, right, which will be AI-enabled and it will be silicon designed, right, because there'll be ultimately a chip that all of us will design in this industry. So this is our workflow. We call it agent engineers, right? So we are halfway through our workflow. We are obviously making progress on the early assistants, right? The knowledge assistants and workflow assistants, so on, right? We are working like crazy on this multi-agent workflow. Everybody's working on it. And I want to end my presentation with that question I asked the panel yesterday. The academics here in the room, right? You guys, I kind of mentioned that you started with custom IC design. When I used to teach VLSI design, drawing rectangles, right? But then the productivity got changed by standard cell design, right? And now with the standard cells, I can enter your design in the gate level. Then you did RTL synthesis, and that was a different way of doing it. But that was what? For the human designers, using the tools to assess the human designer. But the question I am asking to all of you, I don't know the answer. With this AI technology that we have, multi-agent technology, right? Can we make the tools do something different, not the thing that, not fluent for the engineer, right? Not prime time for the engineer, not fusion compiler for the engineer, but a fusion compiler tool for that agentic workflow. And it's this combination of these things, which I don't know how it will be solved. And I think Bay yesterday kind of said maybe it requires AGI. I don't know if it does or not, but that is the exciting challenge. So thank you very much for listening to me. Hopefully it was of some interest, and I'm happy to answer questions. Thank you.
Thank you very much.
Okay, no, I was asked to, okay. Oh my God.
Oh,
the
well,
first
no,
question
hey.
from you.
No, actually, thanks. It was a really great talk. I was curious about the Mercedes example. You were saying that, like, so to build, I guess they're building their own model. Is that what you're saying? Like, they need to do a few simulations to build it? And then, like, how many do they need? And I guess my other question is, like, I guess there must be not so great or it might be a little painful for them. That's why you want to do the physics model so that they don't have to. Can you just elaborate a little bit more on that?
So, great. So Mercedes is just an example, but all the automakers, right, and you and I served on a DAC panel last year, I think I talked about, right? So they are struggling with the design of that. So there are different things that they do, right? I was just giving an example of the external airflow, right? Here is a car, right? And these cars all are very streamlined and so on, right? And exactly how they do the streamlining with the front bonnet and so on, right? And they have a way to minimize that drag, right? If you minimize the drag, this thing is going to go at fuel efficiency of 10 miles per gallon to 12, 13 miles per gallon. That is where they're charged, right? So it turns out that they will slightly tweak the CAD and they'll reduce the drag. They'll tweak the CAD even more and they'll reduce the drag even more, right? But each time they do this, that fluent run takes 10,000 hours. So they can, in a given time, they can only do 10 different CADs, right? Now, so they are not doing the 11th and the 13th and the 14th, right? So if each of those things run much faster, in the same time that would take the 10 runs of the 1,000 hours, I could do 1,000 runs of 1 minute. That's the value. But the trouble is, the faster runs are not necessarily that accurate. So now, Chuck, you, the engineer, will say, how do you guarantee, right? So the assumption is that even though they will be slightly erroneous, directionally it will be the right thing. But if you do these really convoluted optimization maps, you'll get stuck in local media. All the problems that we face in EDA are the same, but that's sort of where the Mercedes is working on it, right? So the foundational model work is, we are working on looking at all the Mercedes models, all the BMW models, all the Volkswagen models, and trying to run fluent internally and massive GPUs, and to build that model so that when Mercedes gives a new design, boom, it'll give a faster thing. That's sort of
Right, but I guess in the example you were saying, so let's say Mercedes is doing it the old way. How many simulations do they need to build that inaccurate model? Like they need at least a few, right?
In that SimAI, they require about 1,000 to build this model,
So you need 1,000 to train to build a fast model?
to train that SimAI model.
Gotcha. So that's the pain. They still have to do 1,000 of those.
Absolutely, but
Okay.
once you do this, Chuck,
Yeah, then.
the remaining tens of thousands of times, right? Now,
Right.
if they do it, here's the catch, right? They train it on the SUV. Now they do it on a boat. It will not work on the boat, right? So they have to redo on a boat. But practically speaking, when you look at I don't know if you have a Mercedes,
No. I have a Ford Bronco. There you go.
but those cars actually don't look that different, right? The S-Class looks like a S-Class, slight variants and so on. So the real world is in the automotive area. It is slight variants. So within that, they are doing tweaks, right? They are just putting the mirror on the left-hand side, etc. And it's incredible, Chuck, how much, if you can save a little bit of drag, long time, that's your fuel efficiency, right? That's why they are doing this. Okay, yes.
Hi, Pablos for Synopsys. In 2016...
Don't ask you. You're a Synopsys. We should ask me offline.
No, but it's good.
Don't get me into trouble here.
I was in Mentor Graphics in 2017 when Siemens bought Mentor Graphics to complete the digital twin. What are the similarities with today and what happened these 8 years that you have learned from? Thanks.
I thought that Ankur would ask me that question. I was so glad that Ankur is not here today and now a Synopsys person. No, I'm kidding. Look, I used to work at ABB and Schneider, and I know that this thing. Siemens actually had, because they bought Mentor, right? They had the EDA, and they had the simulation. Siemens simulation, they have the CAD, the NX CAD. They have the Team Center, which is their PLM. And they have the simulation, right? All the Star CCM Plus, again, Chuck knows, right? So that is a super duper simulation. I should not be praising a competitor, but they actually have all the things, and they have been talking about digital twins, right? So they, in my opinion, right, Siemens has been a leader in digital twins in this story that I talked about. They have been doing it. Dassault is sort of similar because Dassault also has a PLM, 3D experience, and they have wonderful simulators, but they don't have a CAD. They have a partnership with Chuck's company, but they don't have a CAD internally. ANSYS, we had the simulations, but we didn't have the EDA, right? And so now when Sachin bought our company, say, yippee, this is really the solution, right? Because it allows us to build it, right? So this is the opportunity we have in front, right? But it is not fully done yet. I am working like crazy to get this vision that I talked about, right? With Helena's, that HAP, Zebu, etc., the full software verification workflow with the EDA, with this thing, with Twin Builder and so on, right? In different industries, automotive, aerospace, etc., is sort of what I am working on. So, and then customers will figure out whether it's Siemens or Dassault Cadence or Synopsys, ANSYS, that will be the winner. It is not known who is ahead, but it's a great question. And I would say, again, publicly I'm saying that Siemens is actually, they have done this. Now Mike Yellow works for us, right? So Mike and I, Mike Yellow is the chief revenue officer for Synopsys. He used to lead all this at Siemens. He and I talk about it all the time. So all these companies like Dassault, Siemens, ANSYS, Synopsys, Cadence, they're all working on the same problem. But I wanted this group to know about the exciting opportunity of intelligent product design, right? This is the opportunity, right? And I know the physical design is just a small part of it, but the same technologies that you are working on should be applied to solve that entire, much, much harder optimization problem.
Okay. Maybe one more quick question, and then we need to switch to the next session. Go ahead, Lou.
So given that this works out correctly, what should we be teaching in schools? Should we be teaching people to write clearly? Maybe we should be studying literature instead of instead of science if this could be the
That's a
science part?
great question. I mean, last week at the Synopsys Converge conference, I was on a panel, and Igor was there, and I gave an answer to a discussion that John Martinez, a professor from UC Santa Barbara who got the Nobel Prize in quantum this year, he asked a question, so what should we be teaching our students? And here is the answer I gave, and I want to give it here, right? 30 years ago or 50 years ago when computing was with vacuum tubes, right? The way you programmed that thing was in ones and zeros. You had to literally write in machine code. That was ones and zeros was a really hard thing, right? All the numerical methods problems were actually coded in machine code. But then came assembly language programming, where you could write with move, add R1, R2, etc., and the assembler generated the machine code. So in a computer science class, 50 years ago, you were teaching programming with ones and zeros, machine code. Then, when assembly came along, you taught students to do assembly. Then came C, C++, Pascal, Fortran, all the high-level languages, and you taught students to do high-level languages, and you compiled into assembly into machine code. Then came Python, etc., right? And now it is cursor, right? In our world of electronic design, 1985, I mean, Martin Wang, he was telling me, he went into my office and he took out the notes of my VLSI course, right? When I was teaching students about custom design, right? Drawing rectangles, polysilicon over this, right? So the way chips were designed were custom. And then we taught students how to do with netlist, right? With place and route tools. Then we taught students about RTL. So at each level, we have been training students in universities to use the latest workflow. Where I'm heading with this question, it's a great question. I don't think we'll be out of jobs. We'll have to train students in computer science how to write a good code in cursor. Because cursor, as you know, I'm sure you use cursor, everybody uses cursor, right? There are ways of doing the prompt. Writing the RTL, I think there was a question in this thing, right? There are so many ways of writing RTL, and you get different. So, different RTL, you get different thing, right? Because that is tied to the way the Fusion compiler is actually using it, right? So that's a skill that we learned. Oh, this is how you write RTL. So this is how you write programming to get the best out of Claude or Copilot or whatever, right? And the same thing will happen in this world. But that is the world of agentic stuff with the current tools. But the challenge I gave to the whole community is, what if the tools themselves are not set for the humans, right? The tools are for these other things. That, I mean, look, I'm just giving it as a problem to be solved. It's a really interesting thing to look at. But that is the answer to your really important question. We will not be out of a job. Each of us will be a lot more productive, right? So I'll be able to generate a Vera Rubin chip in a month. So when Jensen asks for these things to get to the $1 trillion market, I'll be able to do this much faster. Humans will always be in the loop. Look, I'll be around throughout the day during dinner, so looking forward to the interaction. But thank you so much for listening to my random chats. Thank you.